What if a thunderstorm could briefly do what we normally need a particle accelerator to do? Make antimatter. Not science fiction antimatter in a magnetic bottle, and not enough to power anything. Just a thin spray of positrons, the antimatter twins of electrons, born for fractions of a second inside violent weather. The strange part is not that this can happen somewhere in the universe. The strange part is that the factory can be an ordinary storm cloud over Earth, using air, electric fields, and lightning as its machinery. The case begins with a clue that should not belong to weather at all. A lightning flash ends, thunder rolls away, and for a brief moment, radiation detectors can see a fingerprint at 511,000 electron volts. That number is not random. It is the calling card of matter meeting antimatter. When an electron and a positron annihilate, their mass turns into energy, usually as two gamma-ray photons, each with an energy of 511 keV, flying in opposite directions. So if that line appears around a thunderstorm, the storm has left a very specific trace. Somewhere nearby, positrons existed. Not many, not for long, but enough to sign their name in gamma rays. For decades, that sounded like the wrong suspect. Lightning was bright, loud, electrically violent, but it was still weather. Particle accelerators were machines made of vacuum pipes, magnets, and carefully controlled beams. A storm cloud was messy water droplets and ice crystals. Then satellites built to watch the universe caught Earth doing something unexpected. In the early 1990s, the Compton Gamma Ray Observatory was looking for cosmic gamma ray bursts, the kind that come from deep space. Instead, its BATSI instrument saw millisecond flashes coming from below. They were not from distant galaxies. They were from thunderstorms. These became known as terrestrial gamma ray flashes, or TGFs. Later satellites, including RESI, AGILE, and NASA's Fermi Gamma Ray Space Telescope, confirmed the evidence. Thunderstorms can produce gamma rays with energies of tens of millions of electron volts. Some have been measured above 40 MeV. That is already a startling number. Visible light photons are only a few electron volts. Medical X-rays are often tens of thousands. A thunderstorm gamma ray can be millions of times more energetic than the light from the lightning you see. The detective problem is now sharper. A cloud is not supposed to be a clean accelerator. Air is dense. Electrons smash into molecules constantly. Energy should be lost as heat, light, and chemistry. So how does a storm push particles hard enough to make gamma rays, and then antimatter? The forced layer is the storm's electrical structure. Inside a large thundercloud, rising and falling air separate charge. Ice crystals, hail-like graupel, and supercooled droplets collide. In those collisions, electrons are traded. The exact microphysics is messy, but the result is simple enough to draw. Regions of negative and positive charge build up kilometers apart. A mature storm can stack charge like an enormous, unstable battery. The voltage difference between parts of the cloud, or between cloud and ground, can reach hundreds of millions of volts. In extreme cases, estimates approach 1 billion volts. But voltage alone is not the same as a lightning bolt. What matters locally is electric field, the push felt by a charge at a point. Near sea level, dry air breaks down at roughly 3 million volts per meter. Thundercloud fields are usually much lower than that. Often they are tens to hundreds of thousands of volts per meter. That seems like a contradiction. The cloud's field is usually weaker than the textbook breakdown strength of air, but lightning happens anyway. The reason is that real air is not a perfect, quiet insulator. It is full of droplets, ice, turbulence, and sharp field enhancements. Lightning leaders carve channels in steps, local fields spike, and high above the ground, the air is thinner, so particles travel farther between collisions. Still, ordinary lightning does not yet explain antimatter. The visible bolt is only the biggest clue, not the whole mechanism.
The next suspect is invisible, the runaway electron. Imagine trying to run through a crowded room. At low speed, every bump slows you down. But now imagine that the floor starts moving under you faster and faster. If the floor gives you enough push between collisions, the crowd no longer stops you. You still hit people, but you gain more speed after each impact than you lose during it. An electron in a storm can enter a similar regime. Most free electrons in air are quickly slowed by collisions with nitrogen and oxygen, but a rare electron can begin with a lot of energy, often supplied by a cosmic ray striking the atmosphere. Cosmic rays constantly rain down from space. When one hits an air molecule, it can produce showers of secondary particles, including energetic electrons. If one of those electrons enters a strong enough thunderstorm electric field, it can be accelerated. As it becomes relativistic, moving close to the speed of light, the way it loses energy in collisions changes. The electric field can keep feeding it energy faster than the air can drain it away. This is called relativistic runaway electron avalanche. One runaway electron knocks loose more electrons. Some of those are accelerated too. Then they knock loose more. Over hundreds of meters, the number can multiply explosively. The storm has not built a metal accelerator ring. It has built a temporary acceleration region out of charged cloud, thin air, and a seed particle from space. The analogy is not a railgun firing one bolt. It is more like a steep mountain slope covered in loose stones. One pebble starts moving, hits two others, and within moments a sheet of rock is sliding downhill. The electric field is the slope. The electrons are the stones. The avalanche is the beam. This beam is not visible as a lightning channel. It is a burst of fast electrons, sometimes associated with the early stages of a lightning discharge, especially when the electric fields are rearranging fire. Now the chain reaction reaches the
When a high-speed electron is deflected by an atomic nucleus in the air, it can emit a high-energy photon. Physicists call this Bremsstrahlung, from the German for braking radiation. The electron is not necessarily stopped, but it is bent and slowed, and some of its kinetic energy leaves as gamma radiation. In ordinary life, braking makes heat. In a thunderstorm's particle avalanche, braking makes gamma rays. A terrestrial gamma ray flash can last less than a millisecond. That is shorter than the blink of a camera shutter, but in particle terms, it is a long, crowded event. A single flash can involve enormous numbers of energetic photons beamed upward or sideways through the atmosphere. Satellites often see only the escapees. Gamma rays are absorbed and scattered by air, so the detector in orbit receives a filtered version of what happened below. Even so, from orbit, the signature is unmistakable: short, hard gamma ray pulses tied to thunderstorms. Estimates suggest Earth may produce hundreds, perhaps around 1,000 TGFs every day. Most go unnoticed because they are brief, directional, hidden in storms, or outside the narrow view of instruments. But gamma rays are only the middle of the case. To make antimatter, the storm needs one more transformation. Einstein's equation, E equals mc squared, is often described as matter turning into energy, but it also works in reverse. If enough energy is concentrated in the right way, energy can become matter. For an electron and a positron to be created together, the minimum energy is 1.022 million electron volts. That is exactly twice 511 keV, because an electron and a positron have the same mass. A thunderstorm gamma ray with several MeV, or tens of MeV, has enough energy to pay that mass bill. But a lone photon cannot simply turn into an electron-positron pair in empty space while conserving momentum. It usually needs a nearby atomic nucleus to take some recoil. In air, there are plenty of nuclei: nitrogen, oxygen, argon. When a powerful gamma ray passes close to one, it can vanish and leave behind two particles, one matter and one antimatter. This is pair production. For a microscopic moment, the atmosphere contains positrons made by the storm's own radiation. Some immediately slow down and annihilate with electrons in the air. Others may be guided by Earth's magnetic field lines,
spiraling along them before they die. Satellites have even detected particle signatures linked to TGFs that include positrons reaching space and interacting near the spacecraft. Here, the storm is doing something surprisingly similar to a human accelerator, but with none of the neat engineering. A laboratory accelerator uses electric fields to push charged particles, magnets to steer them, and detectors to read the wreckage of collisions. The thunderstorm version is improvised. The cloud supplies the voltage. The atmosphere supplies the torque. Cosmic rays may supply the seed. Lightning supplies the violent timing. And the detectors, whether on the ground or in orbit, arrive after the fact to reconstruct what happened. The final clue is annihilation.
A positron is not stable in normal matter because normal matter is full of electrons. Once the positron loses enough energy, it finds an electron. The pair can briefly form a hydrogen-like state called positronium, or annihilate more directly. Either way, their rest mass becomes gamma radiation. The cleanest signature is the 511 keV line. Ground observations have caught this kind of evidence in storms. In Japan, winter thunderstorms have produced bursts of radiation after lightning, including signals consistent with positron annihilation. Some of those positrons can come from radioactive isotopes made when gamma rays knock neutrons out of nitrogen and oxygen nuclei. Those unstable nuclei decay by emitting positrons, which then annihilate in the surrounding air. That route is slightly different from direct pair production, but it points to the same deeper fact. Lightning-associated gamma rays can push atmospheric physics into nuclear and antimatter territory. So the complete chain is not a metaphor, it is a sequence. A storm separates charge across kilometers, building a vast electric field. A seed electron, often from a cosmic ray shower, enters the right region. The field accelerates it into a runaway avalanche. Those electrons slam through air and emit gamma rays. Some gamma rays are energetic enough to create electron-positron pairs near atomic nuclei. Other gamma rays can trigger nuclear reactions that later emit positrons. The positrons meet electrons. Matter and antimatter annihilate, leaving 511 keV photons as the receipt. This does not mean every lightning bolt is a dramatic antimatter explosion. Most lightning you see is not making a detectable antimatter beam. The amounts are tiny and the events are brief. Compared with a particle accelerator, the storm is sloppy, unpredictable, and inefficient. But for a fraction of a second, under the right conditions, a familiar weather event crosses a boundary we usually associate with high-energy astrophysics and laboratory machines. The thundercloud becomes a natural accelerator. The lightning flash becomes part of a particle cascade. And the atmosphere, for an instant, manufactures the antimatter version of the electron. The next time a storm passes overhead, the visible bolt is only the surface of the evidence. Above it, satellites may be catching gamma rays. Inside it, electrons may be running away at nearly light speed. And somewhere in that turbulent air, a positron may live just long enough to meet its opposite, disappear, and leave behind two photons that say, antimatter was here. Which part of this chain feels most surprising to you? That storms can accelerate electrons to near light speed? That they can make gamma rays stronger than many medical X-rays? Or that Earth's own atmosphere can briefly create antimatter? Tell me which clue you would want to investigate first.